Okay, this is a video on special cases when solving linear systems of equations. Feel free to pause this video if you want to take notes or if you want more time to process the information. And before you proceed with this video, make sure you've seen the video on solving linear systems of equations using substitution and elimination. Okay, so let's go ahead and begin. So we've got a system of equations here that I want to solve. And it looks like this is set up really nicely for elimination. And I'm saying that because I can see a positive y and a negative 2y here. There's a possibility that I can eliminate the y variable if I can just get this to look like a 2y. I can do that if I multiply the entire top equation by 2. So let's go ahead and do that. Negative 4x plus 2y equals negative 6. So what I've done is I've taken this top equation and I've multiplied everything by 2. Negative 4x plus 2y equals negative 6. And I'm going to leave the other equation alone. Minus 2y. Now I can add these two equations together and I can eliminate my y variable and try to solve for x. But you're going to see that a problem occurs as soon as I do that. Negative 4x plus x is 0. Positive 2y minus 2y is also equal to 0. And negative 6 plus 6 also equals 0. This simplifies to 0 equals 0. And although this equation is true, it seems like that I've eliminated both of my variables. What's going on here? Did we make a mistake? Is there something going on in this particular system of linear equations? And it turns out that the answer is yes. And if we want a clue as to what's going on, what we can do is we can check what these graphs look like when we actually put them on a graph. So let's change these into slope-intercept form. If I want to change this into slope-intercept form, all I need to do is just multiply or add 2x to both sides of the equation. So I'm going to have y is equal to 2x minus 3. If I want to graph the other one, rather than graphing it in standard form, I'm going to change that into slope-intercept form as well. And the way I do that, I'm going to subtract 4x from both sides of the equation. I'll have negative 2y is equal to negative 4x plus 6. And then I'm going to divide both sides of the equation by negative 2. If I do that, this becomes y. Negative 4 divided by negative 2 is a positive 2. And 6 divided by a negative 2 is a negative 3. And what you'll find is that our second equation looks exactly the same as our first equation when it's in slope-intercept form. And that's because both of these equations represent the exact same line. Now let's think back to what it means when we're trying to find the solution to a system of linear equations. We're trying to find what values of x and y can we pop into this equation and this equation that will make both equations true. Or, another way to put it, if we were to graph both of these lines, where would they intersect? Well, if they're both the same line, if I were to graph 2x minus 3 with a slope-intercept of 3 and a slope of 2, I would have one line right on top of the other. They intersect everywhere because it's the exact same line. So we say that there are an infinite number of solutions. Do these two lines intersect here? Yes. There's one line right on top of that line. This xy coordinate will satisfy both equations. That's what it means when we see the 0 equals 0. And if you want, you can try it out yourself. As long as it satisfies this equation, it will also satisfy this equation. For example, pick a value of x, like x equals 3. If x equals 3, then 2 times 3 is equal to 6, minus 3 will give me the value of y, which is 3. But guess what? If I plug in x equals 3 into this equation, I'll get the same value for y. And that's because they intersect at every single point at the exact same time. So in a situation where you end up with 0 equals 0, or any number equals that same number, 5 equals 5, 0 equals 0, negative 8 equals negative 8. Anytime you come up with a solution that looks like this, your ultimate conclusion is that there are infinitely many solutions. Okay, that's it.
Good.